Today we'll look into two topics, which is heat and temperature and calorimetry. First topic is ideal gas. An ideal gas is one which follows certain rules, like P into V can be depicted as nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas which has this much of volume and this much of pressure. Then this is universal gas constant, and this is the absolute temperature. Now, materials on application of heat, they expand. Now look at some of these expansions. If you take a rod, primarily we can call it a one-dimensional body, more or less. Suppose this is the initial length L0. If we heat it from, let us say, temperature T1 to T2, what happens? It expands. It expands by this delta L length. So what we can say, the length of a body at any temperature theta is given as original length before application of heat one plus alpha, and this is coefficient of linear expansion. Theta is the change in temperature. And this change in temperature is from this temperature at which we have taken L0 and at any other temperature theta. So the length of a body at any temperature theta is given as length of the body at any temperature 0 multiplied by 1 plus alpha theta, where theta is the difference between the original temperature at which we took the length and the current temperature at which we want to find the length. Similarly, if we have a body, let us say a sheet of metal, which is primarily an area which has no thickness, negligible thickness, then the expansion experienced in such a body is called superficial expansion. And like linear expansion, this is also defined very, very similar to that, which is A0 is the length at the area at temperature, we can say, let's say T0, at which the area was taken as A0, and this is the area at temperature theta. This beta is the coefficient of beta is beta is coefficient of superficial expansion, and theta is the temperature difference between T0 and T theta. Mind it, this is not a temperature at this, both are not same as this temperature, but theta is the difference between A0 and original temperature and the temperature at which you want to find the area. Similarly here, same thing holds for linear expansion also. Theta is not the temperature at which you are taking the reading. Theta is the difference in temperature between this temperature and this temperature. Is the difference. And there are certain objects which on expansion expand in volumetric fashion. For example, if you have a cube of water and if you heat it, it will expand not in one dimension, not in X direction or Y direction or Z direction. It increases volumetrically in all directions. So that expansion is called cubical expansion. And this is also defined exactly the same way as we have done before. V theta is equal to V0 where V is the original volume at temperature, let us say T0. This is the volume at any temperature theta. Then this is the coefficient of volumetric expansion. And this is the change in temperature between this temperature and this temperature. Okay. Now, alpha, beta, gamma are very small quantities, very small values. So they bear a relation among themselves, and which is beta is equal to twice alpha and gamma is thrice alpha empirically. It is not exactly, but very, very approximately this relationship. The next thing we come to is specific heat. You take any substance, any material, if you heat it, if you supply heat to it, what happens? Suppose its initial temperature was T1, and then after a while, this temperature becomes, or we can say if it is T1, and if it goes to T2, this material has absorbed certain amount of heat. How much amount of heat it has absorbed? This is given by, this depends upon its specific heat, and which is defined as heat that is taken in or taken out will depend upon M S, where this is the mass of the body, S is the specific heat. Now, as we have seen in gas laws, the specific heat has need to be defined whether it is CP or CV, whatever. But in this case, there is no such issue because we are not dealing with gas. We are dealing with materials, solid materials. And this delta T is the difference in temperature. For example, if this body was heated so that its temperature rose from T1 to T2, then delta T will be T2 minus T1. Right? Now, as we see here, when we raise temperature, the materials remain same state. The only thing happens is its temperature changes from a lower value to a higher value. Now, is it possible that we might be supplying heat, but its temperature is still not changing? Yes, it happens when this material will change, it is in the process of changing its state. State meaning it may be, change of state could be what? It could be going from liquid to vapor or vice versa, or solid to liquid or vice versa. During each of these processes, this process as well as this process, while there will be exchange of heat, but the temperature does not change. So related to this, there are two definitions, which is, one is latent heat of vaporization. If we take water in a vessel and heat it, what will happen? Its temperature will rise. If we plot, let us say time versus temperature, its temperature will rise, and then what you will see, at certain time, it will stop going any further. And at this point, you will see some bubbles coming out of the liquid. and getting converted to gas. This is the state where this liquid is getting converted to vapor form. Since we are still supplying the heat and its temperature is not rising, we call the heat supplied to it as latent. Latent means unseen. This is also defined as amount of heat required to change unit mass of liquid to vapor form at same temperature. We are not expecting any change in temperature here. The whole thing happens at a constant temperature. In case of vaporization, this happens at boiling point. Similarly, in a reverse process, vapor can condense to liquid form. Again, heat will be released without any change in temperature for a while. Now, what if solid converts to liquid? We call this as latent heat of fusion. If we take ice in a vessel and again heat it, what will happen? While you're heating, if you notice the temperature, if you plot the temperature versus time, you will see the temperature is not rising at all. And this will happen until all of the ice is not melted. And then only it will start rising when all the ice has melted. So where is the heat going without changing temperature? It is going into changing this ice to water. So latent heat of fusion is defined as heat required to convert unit mass of solid to liquid form without change in temperature. Mind there is no change in temperature, and all the heat that goes in depends upon how much mass you have got. If you take a vessel, put a churner into it, and rotate it vigorously, let's say this contains some water. Initially, the temperature is T1. You keep on rotating with this rotator, this stirrer. What do you expect? You see that if you plot time versus temperature, the temperature slowly rises. Why? We are not heating it. We are simply rotating this churner. So why should the temperature be rising? Okay. What happens when you are rotating this churner? You're putting mechanical energy. Now what happens to this mechanical energy? This gets converted into heat energy. And hence, because mechanical energy is getting converted to heat energy, the temperature slowly goes up. So is there any relationship between mechanical energy and heat energy? Yes, there's a relationship, and which is called mechanical equivalent of heat, and which is defined as W is defined as the work done is J into H, or whatever work we put in, like here in churning, which is in terms of joules, and the result is that this mechanical energy converts into heat energy and produces some calories. So mechanical equivalent of heat is simply joules per calories. How many joules are required to produce 1 calorie of heat? Is mechanical equivalent of heat. Now, when you are doing heat balances, for example, I'm trying to compare a case where I take some water and I heat it. Its temperature rises from T1 to T2. This container may be of, let us say, copper. If I take, if I do the same thing with this, may be of steel, and again I heat it. This temperature goes from T1 to T3, let us say. Then can I simply take the temperature of this and take the specific heat of water to do my heat balances? No, I cannot do that. Why? Because there are two materials involved now. One is water plus the container. Container is also involved. When it is heated together, water is also heated, container is also heated. Now, water will have some specific heat. Let us say S1. Container will have another specific heat, let us say it is S2. Now, getting into this trouble of converting one specific heat to another specific heat, would it not be better if, let us say, the mass of water was we know plus, if we take the mass of water, mass of container, and if we convert into something called an equivalent of water, that means what will be the equivalent of water which will behave exactly like container, meaning thereby, if suppose we take only the container without any water, heat it, its temperature will rise, some heat will be required, and which will be same as mass of the container into specific heat into delta T, right? Now, can we convert this mass into an equivalent mass of water which will behave in the same fashion? Yes, we can do that. Q is equal to M, let us say, the specific heat is 1. Now, if we convert this mass of container or metal or whatever into an equivalent weight of water, then we need not bother about specific heats wherever. We can simply take mass and temperature differences. So we can say water equivalent of any body is equal to equivalent mass of water which will take or give same amount of heat for unit degree change in temperature. I'll simply elaborate it slightly. Let us say the mass of the material, mass of the container is 1, and its water equivalent is, then what this definition says is that whether I take this much of material of container or its equivalent of water, if I heat both of them and raise its temperature by 1 degree, let us say, both will take the same amount of heat. If this one takes Q1, this one will also take Q1. And vice versa, if I lower the temperature, it will give out same amount, both will give out same amount of heat. That is why it is called water equivalent. There is no other purpose than simplifying the calculation and getting to know what is the heat characteristics of this material. More the water equivalent of a material, meaning its heat capacity is more. Because ultimately what will happen is M1, S1, delta T, same as specific heat of water is 1 and delta T is same. So mass of 1 into specific heat of the material So if a body has more water equivalent, that means it's specific, actually it is on account of the specific heat of the material.